Here's an interesting kinematics problem that you can actually find in the kinematics section of the Physics for Olympiad Pathfinder book. And if you want to see anything similar to this in the future, or if you have any suggestions for content, for topics, or specific problems related to maths or physics, let me know in the comments. So let's read through this question. We have a model rocket that is fired from the ground. So I'm gonna draw the ground here like this, and the rocket ascends with a constant upward acceleration, okay, which is unknown for now. And 1 second after the rocket is launched, uh, there is a bolt that drops from the rocket, and we also know that the fuel of the rocket finishes after 4 more seconds. So that's 5 seconds after takeoff. And we also know that the air time of the boat is 2 seconds. And the acceleration of free fall is approximated to be 10 meters per second squared. So we know a bunch of times. We obviously know the free fall acceleration. And we have four options. And this is the kind of question where one answer can be correct, all answers can be correct, or anything in between. So let's try to work through this step by step. So let's try to see how we can maybe find the acceleration of the rocket. And for that, we're actually going to use the boat. And you'll see how we do this. So I'm going to go on to the next page and I'm going to draw how the rocket looks when the boat is dropped. So let's say this is the rocket. And at this moment in time, the rocket is above the ground at a certain height. I'm going to call this height y0, like the initial height, which is also the initial height of the boat, right? Now, I haven't specified this, but it should be relatively straightforward that my y is defined as positive when it's measured upwards with respect to the ground. So anything that is going up is positive. And I don't just mean the distance, I mean velocities and accelerations as well. So at this moment, the rocket has a vertical acceleration a, which the problem says to be the case, but we don't know what a is. And the rocket also has a speed at this point, right? So speed of the rocket, the speed of the rocket at this particular moment in time is given by, let's call this v equals to a times t, okay, because the rocket starts from rest. So using the Suvet equations, we get that the velocity is just acceleration times time. And we actually know what this time is, because this is the time when the boat is dropped. So here's what I'll do. I'll first draw the velocity of the rocket like this. So this is a times t, and I'm gonna draw the bolt. Well, this falls from the rocket, but I'll draw it a significant distance away just to make things a bit more clear. So the moment it's dropped, so until that moment, it was traveling with the rocket, which means that at this point, the velocity of the boat is the same as the velocity of the rocket in this moment. So it's a times t, right? And this t we know to be this 1 second. Okay, because we know that a small boat is dropped from the rocket 1 second after the fire, after takeoff, basically. So this time here is, uh, so let's say t is equal to 1 second, okay, which means that the speed of the rocket here is a times 1 if we put in numbers, and that's going to be meters per second, and the velocity of the boat, or the speed of the boat, is going to be u equals the same thing. So it's a meters per second. It looks like it's acceleration in meters per second, but it's multiplied by 1 second. So one of the seconds from here cancel out. So we actually get the speed, right? So we have that the initial speed of the bolt after 1 second, when the bolt falls off from the rocket, is equal to this. Right. So let's see how we can perhaps use this to find something useful. So we know the expression for velocity of the bolt, for the initial velocity of the bolt. And we also know that from this point, the two accelerations are going to be different, because the acceleration of the rocket is still going to be upwards, and it's going to be a, but the acceleration of the bolt is going to be downwards, and the bolt is going to be in free fall with an acceleration of minus 10 meters per second squared, because g is pointing down. So let's try to describe the trajectory of the bolt, right? So the bolt has an initial speed that's going up. So we can say that y of the bolt is equal to the initial height, which is y0, and then I'll just write the general Suvet equation, plus the initial speed of the bolt times t, plus 1/2 the acceleration of the bolt times t squared. So let's try to put some specific values in here. Let's try to use everything that we know so far. So we know that the acceleration of the bolt after it detaches from the rocket is actually minus 10 meters per second squared. And we also know that u is actually the same as a. And we have a few more things here that we have to be aware of. The first one is the value of the initial height of this y0 here. And we can actually find an expression for that as well, because that's the height that the rocket climbs in 1 second. Okay, and we can find that quite easily. So we have y0 is actually equal to 1 over 2, and then a, where a is the acceleration of the rocket, and then t squared. So if we put 1 for the time, so that is 1 squared, that is a over 2 meters. So essentially what I did was I used the Suvet equation for the rocket, and I used the time of 1 second, which is when the bolt drops. So when the bolt drops, the rocket had climbed up to this height, a over 2 meters, whatever that is. So let's see what we do with this. First of all, this will be replaced by a over 2. And another thing we know is this time and this time, which are the same thing basically. But we know what that is because it says the bolt is dropped 1 second after the firing of the rocket, but more importantly, the air time of the bolt is 2 seconds. Okay, so the bolt, the amount of time the bolt spends in air is 2 seconds. So let's actually write this again, considering everything we know so far. So the coordinate, the y coordinate of the bolt is equal to y0, which is a over 2, plus, and then we have a times t, and then we have minus 10 over 2t squared. So what we know is that the air time of the bolt is 2 seconds. So the air time is t equals 2 seconds. So what is the y coordinate of the bolt in that case when t is equal to seconds? Well, if this is the air time, then when this time is reached, the bolt hits the ground, which means that when the bolt hits the ground, this y value is actually equal to 0. So if we put the value of 0 for the y bolt, that's going to be a over 2 plus a times 2 seconds minus 5 times, and this is going to be 4. So this is one equation with one unknown, so we can find what the acceleration of the rocket is based on how the bolt has been moving until that point. So this gives us, if we move things around, this will be 20 equals 2a plus a over 2, which should be, move it here, this is going to give us 5a over 2, which means that a is going to be equal to 40 over 5, and that gives us 8 meters per second squared. So that's the acceleration of the rocket. So let's see what part A says. The acceleration of the rocket while ascending on its fuel is 8 meters per second squared, which is correct. Okay, it doesn't mean we have to stop here because multiple answers can be correct. So we have to look at part B. So part B says the fuel of the rocket was finished at a height of 100 meters above the ground. Okay, well, now the problem becomes easy because we know what the acceleration of the rocket is. So let's try to find when the fuel of the rocket finishes. So the question tells us that a small boat is dropped 1 second after takeoff, and then the fuel finishes 4 seconds later, right? Which means that the time for the fuel to run out is 1 plus 4, which is 5 seconds. So after 5 seconds from takeoff, the fuel depletes. So if we find the height of the rocket at that moment, that's what we're actually looking for. That's the height we need. So let's see how we do this. That's going to be y equals essentially just a over 2t squared. And if we put the numbers in, so we have the acceleration is 8 over 2. The time is 5 squared, so that's going to be 4 times 25. And we got this as 100 meters. So 100 meters above the ground, the rocket runs out of fuel. And let's see what we have here. Fuel of the rocket was finished at a height of 100 meters above the ground, so this is also correct. Let's see what C is telling us. The maximum speed of the rocket during its flight is 40 meters per second. Now, when would this maximum speed actually occur? That's the first thing we have to consider. So, until this point, the rocket was running on fuel, which means that it was accelerating with this upwards acceleration of 8 meters per second square. So let's try to maybe draw this out in a certain way. So this is the rocket, and this is, let's say this is just before it runs out of fuel. So just before it runs out of fuel, we have got an acceleration of 8 meters per second square. So as long as this acceleration is here, the velocity will keep increasing. But the moment this acceleration disappears, that means the fuel is gone. So when the fuel is gone, this acceleration is no longer here because there's no more thrust. So from this point on, if you want just one moment after this, 1 millisecond or less than 1 millisecond after this, the rocket is now subjected to free fall, similar to what was happening to the boat. So the moment there's no more thrust, the moment there's no more fuel, the uh, the acceleration will be downwards, and it will have a value, an absolute value of 10 meters per second squared. So from this point onwards, the velocity will decrease, and until this point, the velocity increases, which actually means that the maximum value of the velocity occurs at the height when there's no more fuel, which is the height of 100 meters. So we just have to find what is the velocity when the fuel depletes. So to do that, we're going to use the Suvet equation for velocity, which is v equals u plus at. And we know u is 0 because the rocket starts from rest on the ground, which means that Vmax is going to be equal to 8, that's the acceleration, times 5 seconds, which is how long it takes to run out of fuel, and that's going to be 40 meters per second. So that's the maximum velocity of the rocket, and from that point on, the velocity will start to decrease because the rocket will be subjected to a negative acceleration. So let's see what C says. Maximum speed of the rocket during its flight is 40 meters per second. So it turns out this is also correct. And finally, we have something referring to the total airtime of the rocket, right? Now we know the total airtime of the boat, but we also have to find that of the rocket. And this says it's 15 seconds, so we have to check whether it's true or false. Right, let's see how we can do this. First of all, I'm going to draw the rocket again. And this is the rocket just after the fuel finished. So this is my rocket, and at this point, I know what my initial, I'll call this the initial speed of 40 meters per second, and also there is a negative acceleration of, let's call this minus 10 meters per second squared. And the reason I'm being aware of the minus sign now is because I'm preparing this situation for the two-vet equations. So let's try to find what is the Suvet equation for the rocket from this moment. So we know this height as well, actually. So this height was found in part B, I believe, which is 100 meters. Okay, I'm going to call this y0. It's a different y0 than the previous one. So this is the height at which the fuel runs out. So if we write the Suvet equation for this, we get y equals, and then we have y0 plus u times t, and then plus 1 over 2 at squared, where now we're just going to substitute everything in here. So this is going to be 100 plus 40 times t, and then this is going to be minus 5t squared, right? Because a is minus g, just to make a work, a is equal to minus 10 meters per second squared, rather. Okay, right, so this is the time measured from the moment the rocket runs out of fuel. So to find the total airtime of the rocket, we basically have to measure the time until the rocket hits the ground. So when the rocket hits the ground, that's when the y of the rocket is going to be equal to 0. So in other words, if we substitute y equals 0 in here, we should get the total time from this point until the rocket hits the ground. So let's do just that. So this equation becomes 0 equals 100 plus 40t minus 5t squared, and we can cancel out a couple of things. So this is going to be 20 plus 8t minus t squared, and I'll rearrange it because I don't like minus on my square term. So this is t squared minus 8t minus 20 equals to 0, and this is just a quadratic equation which we can easily solve. So you can find the discriminant as being 64 plus 80, which is 144, which is nice because this is 12 squared. So T12 is 8 plus or minus 12 over 2. So T1 will be 8 minus 12 over 2, which is minus 2 seconds, which doesn't make any physical meaning. Doesn't have any physical meaning whatsoever, so I'll just cancel this out. And then the other one is going to be 8 plus 12 over 2, which is 10 seconds. So there are 10 seconds from the moment the fuel runs out until the rocket hits the ground. So let's now find the total airtime of the rocket. So we know that the small boat is dropped 1 second after takeoff. And then 4 more seconds later, the fuel runs out. And then we just found here that after 10 more seconds, the rocket hits the ground. So the total airtime of the rocket is therefore going to be 15 seconds. And that is telling us that D is also correct. So for this question, all 4 answers, all 4 options were correct. And that's the end of the question.